All right, ladies and gentlemen, we are going to discuss fractional distillation. And here we go. Here's a worksheet for us. You get to keep this worksheet. It's not an assignment. You should have a copy in green. And the question here is, why is it necessary to do fractional distillation as opposed to simple distillation? I guess before we answer, what was simple distillation? Anybody? Yes.
Separation of liquids with boiling points over 100 degrees.
Close. She said separation of liquids with boiling points more than 20 degrees Celsius separated from each other. That would be a, oh, sorry, she was answering fractional or simple, and I answered fractional. Tweak that. Simple distillation, the boiling points are different by more than 20 degrees Celsius. And we have guaranteed that we have an even greater distance between the boiling points by changing the chemicals in experiment 3D. So, when is it necessary to do fractional distillation? When the boiling points of the liquids, let's just be general, are close. Usually within 20 degrees Celsius of each other. And that needs to be a superscript. There we go. Answer to a question. Bold and red, of course. Okay. What is a theoretical plate? Another good question. Anybody?
It's a cycle of evaporation and condensation.
Perfect. A cycle of evaporation followed by condensation. So I always want you to get inside the distillation itself. Pretend you're one of the molecules. What's going on? You're in a liquid state in the beginning, right? Liquid state. You heat up a liquid. That always creates more vapor than you used to have because your liquid, your molecules have more energy now. If they have more energy, then more have energy enough to overcome intermolecular forces. And when you do that, overcome intermolecular forces in the liquid state, what happens? The word's on the screen. Evaporation. So that's happening. So where do these vapors go? When they're created, you're boiling in a flask. Vapors are in the liquid's down at the bottom and the vapors go above that, right? We saw that last week. And you actually saw them then condense down back into the flask. You saw this. I made you look for it, right? Yeah. So you were seeing at least one cycle of evaporation and condensation. Maybe more, you can't tell. Okay? And then once you've evaporated and then condensed, now you've got the condensate on the side of the flask, right? It's up a little higher. That's hot there too. Hopefully hot enough. It will eventually be hot enough to boil that new mixture. Okay? The new mixture in the new condensate has a different composition than the old mixture at the bottom of the flask, right? And to further our discussion here, these two expressions, I want to use them, but I can't because we don't know what they are yet. MVC and LVC. Anybody want to take a stab at what those are? Somebody new?
It's like most volatile.
Yes. Most. I will accept many C's here, but you got to have most volatile compound chemical components. They all start with C. Chemical, compound, acceptable, component, acceptable. Now, just summarize for me, if you're more volatile than the other chemicals, what properties are you going to exhibit that's different than the other chemicals? I like it. There's two teams in stereo almost. A little delay, a little reverberation. Low, good. Over on one side of the room, they said they evaporate faster, the more volatile chemicals. And over here on this side, we had a gentleman say lower boiling point. They go hand in hand, don't they? Lower boiling point's going to evaporate faster than higher boiling point. And I don't need a dash there. Oh, yeah, lower BP, more, how do you say it evaporates more easily in chemistry talk? It creates more vapor pressure. But I will use those words you use too. Evaporates more easily. Be nice if it was on one screen here. It's not. It's hard to read now. Yeah. And of course, yeah, red. Oh, that's pretty nice. I like that. Copy. Paste. Get rid of this extra space here. Least. There's Q in there. You didn't know that, did you? Least volatile chemical. That's LVC, right? Yeah. What about boiling point? Higher. With a W. Also not well known. More, no, not more vapor pressure. Less evaporates less easily. There you go. Groovy. How can more theoretical plates be achieved practically? Explain the theoretical. Oh, yeah. Okay, here we go. No. Actually, these diagrams are part of my answer. Down here, I guess, I can't scribble on this screen, okay, everybody? So bear with me. Below is a, what do you call that? Object. Pictured right here. A spinning band. It has grooves. You see the grooves? This is going to be awkward. Tab, return. These grooves create more. What's the, oh, she knows the magic words for distillation are always surface area. Surface area. Tab, return. I didn't get the tab, did I? This allows for more, hey, surface area. What happens on the surface of the glassware? You're boiling liquids, and then what happens on the surface? More condensation cycles. Okay, tab, return. The spinning action, and I don't know, I'm going to stop the share and try to do a demo using the camera. Here we are. Here it is. My question for you, when this thing is spinning, and it will spin in this direction, Which way is the liquid going when it's trapped in the grooves, up or down? If I'm here and it spins down there. It's spinning this way. Convince yourself there's a downward action to the grooves going this way. Downward. So you're actually returning liquid to a lower place so that it can get heated up and evaporated again, maybe even condense where it condensed the first time, but it's a new cycle, isn't it? In the same volume, because you returned the liquid to a lower place. Nice. So I'm going to write that on the answer. I think my answer is here. The spinning action also returns liquid, tab return, to a lower, you think that's a new line, to a lower position, which also allows more theoretical place. Okay. Nice. Okay, what about below? Below are two. Now these are tall pieces of glass. Both of them. We call those fractionating columns. Below are two fractionating columns. Their height gives them more surface area, which gives more TP. Now you can't do that when you're writing stuff and have an initialization and you haven't explained it. I use theoretical plates somewhere, right? There it is, TP. There you go. Forgot my game plan. The one on the left is packed with glass beads. Often metal mesh like copper or steel wool. I don't even know if anybody knows that expression anymore, steel wool. You can buy it, like scrubbing pad. Yeah, okay, still use it. Okay, cool. Also can be used. Often metal mesh like copper or steel wool can be used instead. This clearly creates more what? Yeah. SA. Surface area. Surface area. And thus. Oh yeah, thus. We don't use thus enough. More TP. Good. Their height gives them more surface areas, gives more TP. I'm going to add, then I can't add there. I don't have tabs marked. Really tall columns can be found in oil refineries. Refineries. where, whoa, this one's going to be fun. Well, what do you refine in an oil refinery? What's the raw material they're refining? They get it out of the ground and it's impure. What's the word for impure in chemistry? Crude. I love the way she said that. Yes. Really tall columns can be found in oil refineries where crude oil is fractionally distilled. Now, these columns can be many stories tall. Many stories tall. Like this building. They could be as tall as this building, which this is a 4-story building here, on this part anyway. So you can imagine a lot of theoretical plates there for that. We good? All right, now sadly, I forgot to do something and I need a few of you to jump on it in the background here. If at least each team has one Aldrich catalog, that's going to help our next exercise. So I need people to go in the back room and get a red Aldrich catalog for each team. Please get the 2010 one. Most of them are 2010, but I want us all working from the same book. You'll see it on the spine, 2010. And while we're waiting for them to return, let's look at our exercise here. I sure hope it switched over in the video. We'll see. We could be talking with the other screen here and just words and nothing happening. But this has happened to me before. I'm not taking a chance. Stop share. Share. I know it's coming back where I want it this time, but I did it wrong. Stop share. Share. I need it over with paint. Thank you. We have work to do. Down here. We need to use this graph. And the only way to use this graph is if you know what measure of the mixture. Don't tell me it's about knowing the temperature of the mixture. No, no, this graph's about knowing the mole fraction of the mixture to predict the temperature on the liquid curve and on the vapor curve. When you heat something, the liquid becomes a vapor. And the temperature of the vapor is related to the temperature of the liquid, just like in a mixture of, let's do 2 different phases, water and ice. Game of Thrones reference there. Mixture of water and ice. I can tell you if you throw a thermometer in that mixture, what the temperature is. How can I do that? I know a mixture of water and ice will always have a temperature of 0 degrees Celsius. Similarly, when you boil a liquid, it boils at the temperature that's called the boiling point, and the vapor above the liquid has the exact same temperature as the boiling liquid, just like the mixture of ice and water. The cubes were at 0 degrees Celsius. The water was at 0 degrees Celsius. In a liquid that's about to boil, the vapor above the liquid has the same temperature as the liquid. Got it? Now let's get to work. What data do I need about methanol? And I need you all to try to find methanol in the red book. And somebody, the first person that finds it, yell out a page number so we can all get on the same page. It's under METH. And while we're waiting, we're going to need the density. And I'll try to type on here. This could be an adventure. Good old typing with paint. 1753 is the page number. And I need the density. You've got it right there. D says 791, and they might not have the units, they might, but we're supposed to know them. Don't look at the book. We're supposed to know the units for density, like we're going to use them anytime, any day, without notice, without warning. What are the units of density for a liquid? Grams per milliliter. Give me two other ways to say milliliter. Centimeter cubed. We always forget the way the doctors say it. cc. Oui. Okay. I need the formula weight or the molecular weight. They are indeed the same thing. I believe Aldrich likes to call it formula weight, don't they? Correct me if I'm wrong. Does it say MW or FW? Neither? FW, what's the number? 32.04. What are the units for molecular weight or formula weight? That's the proper one we use for real life practical chemistry. Grams per mole. Okay, that's our research. We're not going to do research on the water. But we're going to need the density from your memory. We're supposed to know that one.
1 point.
Just go 1.00. That'll suffice. We're using 3 sig figs above, so 3 sig figs should work here. And units are grams per milliliter. Formula weight, you can give me 4 sig figs on that. 18.02. Periodic table, 2 H's, 1 O. All right, let's do the methanol to the right. If you're going to find mole fraction, tell me the steps. We have to go mole fraction or this graph is useless to us. So we don't have mole fraction. What's the steps on the way to mole fraction? Start with the milliliters. I like it. This is where I fell in love with chemistry. We're going to start with milliliters and then use conversion to get rid of milliliters. So I have milliliters on the bottom of my conversion. And I have information here to go to what amount? Density lets us go from milliliters to grams, which is mass. And once you go grams, what can you go to? Moles. How do you do that? From formula weight, molecular weight, yes. And once you get to moles, you're halfway to mole fraction. You got to do moles of substance 1, which is methanol, moles of substance 2, which is water, and mole fraction is moles of substance 1 over total moles. That's mole fraction for one substance, and mole fraction for the other substance. You can do 2 ways. 1 minus the answer you just figured out, or moles of substance 2 divided by total moles. They'll give the same result. So methanol we're doing right now. The amounts you're given, 423.7 milliliters. Times. Something that gets rid of milliliters. Oh man. I'm not going to have numerator denominator here because I can only type. Sorry. I'm going to put in 0.791 grams per milliliter, and you tell me where I'm going to be when I'm done with that part of the calculation. What units are you going to have? And you can go ahead and start the math on that. I'm going to be, what am I going to have for my units when I'm done? Grams. I got to get rid of grams, make it into what? Moles. There's 1 mole for how many grams of methanol? 32.04. And I need 2 people to calculate that using their calculator because I need to have verification on the result before we move forward. I'm eyeballing it. 0.791 is 3/4 of 423. We're in the 300 range. 300 divided by 320. We're in the 10 range. I'm looking for an answer close to 10. And this is what I do every time I do a calculation without numbers. That way, when I get a really screwy result, I know something was done wrong. I'm looking for an answer near 10. Was I way off? 10.46. Units, please. Mole. Try to squeeze that on a line here.
I bet the casinos don't like you.
Oh, I don't do that stuff. Come on, man. He said, I bet the casinos don't like you. I got a friend that loves the casinos. He uses such rational thoughts, yes.
The eyeballs it too?
You got to keep the eyeball, you got to know where you're at, right? Anyway, enough talk about that. What about the, whoa, I need you to be taller. Let's go. How much water did we start with? 1,100. Yeah, 96.2. Wait, that's not the number up there. There was a conversion done there. You're not going to make me do it, are you? That's one you guys are good with. Milliliters and liters, you better be fast. Because that one you're going to, no matter what, in this room, any health career person, milliliters and liters, and grams and milligrams, going from milli to without the milli, essential. Mistakes, unacceptable. People will get hurt. Drug doses, almost always in milligrams. Balances used to measure these drugs, almost always in grams. Okay? You better be putting the right number of grams in there. Anyway, I go on a little bit. Times, same idea, but 1.00 grams for every milliliter times 1 mole for every 18.02 grams equals how many moles of water? I'm eyeballing. I got 1,200 divided by 1,800. Well, 1,200 divided by 24 is 0.00. It's tough because I got decimals I got to move in my head too, and I'm getting nervous. What you called it, 20-ish? Okay, what do we got? 66.38. Did somebody else get that as well? Then I'm happy. That's another way to do eyeballing. So, I'm not saving. Maybe I should, huh? Worksheet T. There we go. Yeah, we're not ready to use the graph yet. What is the symbol for mole fraction? Say that again. She said it right. Oh my goodness, it's been years since I've had a student guess how to say it right. Most students say X, but she said pi. Yes, pi, C-H-I. And it looks like an X, but I don't think that's going to get me the right font. I think I might have to go with the C. Let's see. The learning experience for me too. We need the symbol font. And that is definitely not what I'm looking for. That was with the X. It's the C. Capital letter C on your typewriter. I teach more than chemistry. Capital letter C on your typewriter. Change the font to symbol. Remember, they never tell you. Why didn't they just call symbol Greek? I don't know. But you need to know eventually you're going to write a paper for science class and you need to use your computer. Symbol font is Greek. So moles of methanol divided by total moles. That's 10.46 plus 66.38. And we're looking at like 1/6, right? 1/7. 0.15-ish is a real crude approximation, but I might be off on that. Not bad. I said 0.15. I was ballparking pretty decent there, and she said look, hold that thought. Say it again, 0.36. How about 4 sig figs just for fun? 6.1. And notice it was moles over moles. I think I can get them in there. Moles over moles. What units do you have in your answer? Wait, what do I hear? What do I hear in the tiles? It's gone. We were talking about this earlier. But help me. What's in the tile up there today? There's a cricket. A cricket's up there, and he doesn't behave apparently. But that was the correct answer for what are the units here? Crickets means nothing. All right. Because they canceled. I can't get that mole in there. It's a mess. Suggestion? Move it to the left. Look at that, to the left. Beyonce solved our problems. Okay. And that's for methanol, right? And I think that's all I need. I don't really need the mole fraction of water because I can use either one. Just remember, this is for methanol. Now we're ready to use graphing 101. So when this question comes up on your midterm, you best be in possession of a ruler, okay? Because I need this to be read accurately. So I need to know first, mole fraction of methanol is this direction, correct? So this first line is 0.1. Do we agree? Yeah, because there's 10 of them. 0.15 is right there. 0.136, a little to the left would be 0.14. 136, just a hair to the left of that. I'm thinking about right there. And I'm going to get my line drawing tool. I had it a second ago, but I lost it. Probably on the home page, right? And I got my line tool, and I'm going to have it super thin. And we like super thin. And how about orange? 0.136 was about right there. Do we like where I put that? Now I can see when it's vertical because I don't have any edges on the line there. There. That's where it intersects the liquid curve. And the question is, what is the boiling point of the liquid? That's how I knew to stop at the liquid curve. And this is just graph reading 101 now. I'm going to do a little blue line. I already got a blue. Oh, I changed the color because that's the one I just did. Oh, no. Okay, never mind. I want to draw a new line. This time it's going to be green. And I'm just going to read it across here. That's horizontal. Answer A is right there. And I need to type answer A. Graph reading 101. What do you got? 90, 95. There's 92.5 in the middle. 92.5, 92's there. That looks like almost 91 on the button, doesn't it? Thoughts? I like thoughts. Okay. Select. I can't select my line. I wish I could. I was going to draw 4 more of these. 1, 2, 3, 4, and see if they're evenly spaced. It might be a hair more than 91. Anybody want to take a stab? Yeah, I won't go with the 0.5, but the 0.3 I'll take. I'll take a little higher than 91, but not too much. All right, so answer to A, I got to start over. 91.3. degrees C. And I go, I don't have a superscript option on paint. I'm gonna go DEG. There you go. You're allowed to do that. Save. Did you get a higher answer on your graph?
Yeah,
Much?
around 94.
Oh, yours is way up there. You started here, 0.136?
I made sure it's perpendicular.
Yeah. Huh. Yours is, okay. You may have started on the other side of half on this one. Maybe. We're left of half here. You may have started right of half. No, that would make it lower. No, you started a little too left, I think. Because that's up higher here. Okay, so we got A, we can type it again here. What was it, 91.3? Big. My computer's talking to me. Saving. Okay. Now, what will be the composition of the liquid after two theoretical plates? Well, here's the deal. Remember what I said about a boiling liquid? We're going to start theoretical plate number 1 in red. You boil a liquid at the same temperature as the vapor above the liquid. It's happening at the same temperature. So that's horizontal, people. Theoretical plate number 1 is about to start. Right, going from here straight across until the vapor becomes, sorry, the liquid becomes, and I gave the answer away by mistake, vapor. Well, paint has this nice feature that there's a little crosshair where the line leaves off. 1+. Okay, so that is evaporation number 1, isn't it? Evap. Jeez. Number 1. And what happens after the evaporation? Well, it finds a piece of glass or steel wool or something, and it condenses, doesn't it? And when you condense, you go from what phase to what phase? From gas, which we're at right now, to liquid, which is the other curve. Okay, so we're taking a mixture that's a gas and cooling that entire mixture so it's a liquid. So the mole fraction of the gas has to be the same as the mole fraction of the liquid. It's the same mixture. So I'm going to take that from line tool, and straight down. So far, so good. So this is theoretical plate number 1, ending right there. Ah, I don't like that. Straight down, straight. Don't you bend on me. Thank you. And that's condense number 1. Condense number 1. Number 1. I can't move stuff on this thing. Control X. Got to be about right there. Does that work for you? Okay. Now we want to do 2 theoretical plates. So you're going to take this new mixture that you created here, that's a liquid. Question before we move on. Is the mole fraction of methanol higher or lower now? Higher. Why? Try to use these two in your answer. MVC and LVC. When you boil a mixture, which one boils to a higher extent? MVC, so you create a higher ratio of more volatile component in the vapor than what you had in the beginning. And then you condense that, and it's higher in the more volatile chemical, which in this case is methanol. Now we do the same deal. We'll do a new color, go brown with our line tool. Start there. There's going to be evaporation number. I started perfect there. Evaporation number 2. And condensation number 2. I want a new one, dude. Okay. Straight down, stopping right there. I'll type it in. Evap number 2. Condense number 2. That's your second theoretical plate, isn't it? Both answers lie at the end of the second brown stick. One of the questions is, what is the composition? Which axis has the, why did it move condensed number 2? Why is this happening? I gotta click out the box. First, I gotta get condensed number 2 where I want it. And that's not happening. Whoa. That was good. Click out the box. Thank you. And yeah, the down here is the fractions, right? Composition is mole fractions. So blue line for reading stuff. I'm gonna take it straight down. This is the answer for B, correct? Straight down here. And that's 0.7. There's 0.75. I'm thinking 0.76, aren't you? 0.76? Yeah, I like it too. So I'm going to write that here. B, no, B. Symbol, I think it was lowercase c. Maybe it's uppercase. Uppercase C, methanol equals, what did I say, 0.76? And I want that to be what font? I'm even testing you on that. Symbol font. Let's go to T's. You'd think I would have figured this out over 30 years. Don't go to S's. Symbols at the end of the S's. Go to T and then go up 1 or 2. See, watching your teacher learn. Oh, the lowercase one looks more scripted. It looks better, but I can't change it. So B, it's a lot more high percent methanol, isn't it? We went from 0.136 to 0.76. Vast improvement, right? And then the answer for C is just read it from here across. Right there. Whew. That is over 69, isn't it? I would think 69.5 would be a pretty good guess. What do you think? Yeah, because 67.5 is here, 68.5 is probably right there, 69. Yeah, let's go 69.5. And we'll type that as our answer for C. Hard to read that. Oh, it's still on symbol font. Times New Roman also close by. C. What did I say? 69.5, right? 0.5. Dag C. Save. Here we go. 69.5. Big C. And here we'll go. Chi of methanol equals 0.76. Wrong color though. Oh, it doesn't let me edit. I had the wrong thing there. Bear with me here. There's more than one way to fix a mistake, right? Going with this old technology. Little thicker on that 10. Ah, X marks the spot. Should be Chi marks the spot. Good place to end the video. Save. I'll be posting this online as the accompanying document for this video.
I was just gonna ask you.